Hey everyone, let's get started on today's lesson. So you ready? Maybe, maybe not. Well, if you had a little bit of indecisiveness in your thoughts, that is what we are going to call uncertainty. And when it comes to uncertainty, that happens a lot in science and measurements and any sort of data collection. So, why is uncertainty important? Well, uncertainty important is because we can't always be precise. We can't always be the most accurate. So, what uncertainty allows us to do is to be able to say with a little bit more confidence what our values are, or report values with confidence, you could also say. So, as we report values with confidence, we know that measurements can be as precise and as accurate to a certain degree as we want them to be. But more often than not, it is going to be based on our measuring tools. So they'll be initially based on our measuring tools. So what do I mean by that? Well, there's a ck12.org there's an activity for that I'm not requiring you all to do, but it is one that is very useful for people who are not quite fully understanding it. Just remember my CP class. If you look into the resources tab on facts, you'll find the link to the access code to CK12. And for my honors class, we'll be using other methods of online tracking and learning, but that's still a possibility for you guys to use. So it'll be a whoopsie. I forgot there's the little big button. So CP required. Well, CP account required. But if you need any help logging that in, logging into that. Feel free to ask, but if you need any help navigating the site, there's a video as well, so you should go check that out if you're wondering. So for uncertainty, we're going to report values with a certain confidence, and the initial uncertainty is going to be based on our measuring tools. The way that we are going to write uncertainty is based on two different factors. So you're going to have some measurement, and then you are going to say that's going to be either plus or minus. I know my T looks like a plus sign, but bear with me there. Plus or minus your uncertainty. And for the honors class, where propagation is going to be a thing, this is going to be really important. But when we're doing just significant figures, then that's not going to be as important. This is just going to be sort of for if you are having a measurement rather than a calculation. So whenever you are reporting an initial measurement, you should always put at least some sort of uncertainty. So, for example, this would be your distance x plus or minus this little delta x. This delta is your uncertainty. So if you're taking a measurement, it'll be 3.2 plus or minus 0.1 meters. So that means your measurement is going to be 3 meters, 20 centimeters, plus or minus 20 centimeters. So that's a pretty big, plus or minus 10 centimeters. That's a pretty big gap in terms of how uncertain you are. But with that large uncertainty means that your measurement is more likely to happen, or more likely to fall in between those ranges. So for your lab activity, I'm not going to go over it yet because I still want to go over a little bit of intro. But if you're taking a look at the meter sticks that we use, or more specifically the calipers that we use, let's take a look at the meter sticks first. Come on. There it is. So this is just a stock image of a meter stick and a yardstick, but this is to help you get a better idea of what it means by uncertainty. So let's say you're measuring from 0 to right around there. So 0 to right around there means that it looks like it's going to be in the 2.1 centimeter mark, but then you're going to be uncertain of that last digit right there. You know it's 2.1, but what is that last digit? Well, you're kind of uncertain. So with that being said, this measurement is going to be 2.1 plus or minus 0.01, or depending on how confident you feel, whether that's a 0.5 or a 0.4, you could easily just say that it's going to be plus or minus 0.05 millimeters. Because each of these little ticks is a millimeter, it says, and we're trying to determine what the uncertainty is. So you have one less digit, so there's 2.1, but then it would be safer to say that you're uncertain between the nearest half a millimeter, because you can't really go too much by tenths, but going by ones is a little bit too big of an adjustment. What about, these are more of the calipers that we'll use for the lab, and I'll show you that in another video sometime, just because of the recording equipment here and the fact that I don't have my calipers here. So, and in fact, I want to make a separate video for that as well. But let's say we're going to be using millimeters here. Here, with this measurement, what it is you're going to take whatever value is going to be above that 0, and that's what your measurement is. So it looks like it's going to be 22 about millimeters. But then in order to get a larger number, then a more accurate number, we have to figure out which one of these smaller lines lines up perfectly with another line above it. So this looks like the 2 works. So what this is it's going to be 22.2 millimeters. And then your uncertainty luckily it's given. Your uncertainty is going to be plus or minus 0.05. So for your calipers, and switch over to a different color. So your calipers, ooh, that was not the color I was wanting. That was 22.2 plus or minus 0.05 millimeters. Whereas for the meter stick, we know that was, let's go back to that. There we go. We said that was 2 point, I believe it said it was 2.1 or 2.2, but that uncertainty is plus or minus half of a millimeter, not necessarily a 20th of a millimeter. So that would be, in terms of millimeters, this Shutterstock image is not the greatest because these are actually being centimeters, but you'd be accurate to the half a millimeter rather than the 20th of a millimeter. So we said for the meter stick, that was 21.5 plus or minus 0.5 millimeters. I just converted it into millimeters just so we can get a little bit more of a better representation. So if you think of it, the measurement that we had said for the calipers, we are going to be a lot more confident about what our value is up to a better measurement, rather than for the meter stick where we're not so confident about our measurement. And that makes more sense because the calipers, of course, are used to measure, are precision instruments. So they're used to measure things up to a smaller decimal point rather than the meter stick. So what happens though when you have the, let's see if I can change the correct color this time. There it is. Let's say what happens when you have, this is a bad square. It's not good. A box. Oh yeah, that's not good. Bear with me there. And you're measuring something with calipers and one with a meter stick and since we're accurate to the 0.05 millimeters, we need to make that a 0 right there. But what happens if we're measuring and this length is that 22.20 plus or minus 0.05 millimeters, and that one is 21.5 plus or minus 0.5 millimeters. So what happens if we were to try to find the area of this, just this side? What happens if we're trying to find the area of that, but we have an uncertainty here and an uncertainty here? Well, there are two ways of going about this. One is for the simpler route, but the other is the more mathematically involved, but closer to what scientists use when doing measurements. So the first method involves significant figures. And you might remember significant figures from chemistry last year. And the other method involves the law of error propagation. So I'll take a look at what the significant figures method is in this video, and then I'll open up a law of error propagation video for the next one, just because I don't want this video to be super long. So significant figures. Significant figures for us are going to be useful in determining a more broad measurement. And so what do I mean by that? Well, let's say we had our area problem again. And this happens there are certain rules for significant figures themselves and certain rules when you add or subtract numbers with different significant figures. I'm going to focus on just multiplying and dividing. Because I don't want to distract you with some other things that you're not going to need as of now. But just know that there is a different methodology to it. So you have your two measurements. Let me go back to them real quick. So 22.20 and 21.5. So that was 22.20 and then 21.5 millimeters. And even though there was uncertainty, we are not going to be using those uncertainties in our calculation. Those uncertainties will only help us with the number of significant figures that we have. Well, helping us write out how precise and accurate our numbers are. So, whenever you are multiplying and dividing significant figures, you want to keep the least number of significant figures. So what does that mean? Well, let's break it down to a typical math problem. So you want to find the area of this, and I know we've done a lot of problems finding the area. So you want to find the area of this. All you do is do length times width. So 22.20 times times 21.5. And then let's go up my tools, math tools. Well, should be a calculator here. Math tools, rulers, that's where a protractor. Is it in desktop tools? Interesting. Must have changed versions. Regardless, let's go back to the flip chart, and I'll pull up a calculator real quick. This is my different computer. I don't have my emulator on there. So let us plug in 22.20 times 21.5, and you get 477.3. Why would that be 0.3 though? So, okay, it's probably 477. All right, so that's going to be 0.3, 477.30. But as we said, when we are multiplying or dividing, we're going to keep the least number of significant figures. So we know that 22.20 has 1, 2, 3, 4 significant figures. And 21.5 has 1, 2, 3 significant figures. So we want to keep the least amount. The least amount between 3 and 4 is, of course, 3. So this, unfortunately, though, has 1, 2, 3, 4, 5 significant figures. So we need to bump this thing down. And the process in which you do that, the easiest process that I have found, if you have found a simpler process, feel free to use that. But what I have found works the best is to get it into scientific notation first. So 477.30 is the same as 4.7730 times 10 to the 123. And that means that our, that still has 5 significant figures, but it's pretty simple to get it down to 3. All you do is look for 3, so 4.77. And then, this 3 makes it round down, so we're just going to be left with, this goes away, we're going to be left with 4.77 times 10 to the third millimeters cubed. So, why that's important is that we can say with a certainty, with a degree of precision and accuracy, well, not so much precision, but with a larger degree of accuracy, that our measurement is going to be sorry, that's 10 to the second. I'm just realizing that. I was like, something didn't add up. Well, let me do a little. Come on, little pen. Make it a little nicer. Get my 3's mixed up. So it's 4.77 times 10 to the second power. That's times 10 to the second power. So we can say with a certain degree of accuracy and with a certain degree of confidence that the measurement of this area right there is going to be 477 cubic millimeters. And that's a fair degree of confidence because I'm still getting used to my thing. Right. So 477 millimeters cubed. So, I'm still doing that again. I'm thinking 3D. Three-dimensional, but we're sticking to 2 dimensions. So, if you think about it, 0.3 millimeters squared, is ridiculously small. So to say that whatever our measurement is, with a certain degree of uncertainty that we have, with the lack of precision that we have, the lack of repetitiveness that we have, we can't say with certainty that this 0.3 is going to be in there. Because that's saying that it's going to be 477.31. It could be 477.29. That's showing that we are confident to the hundredth of a millimeter squared, which is, with the tools that we're given, not very likely. But when we say 477 or 4.77 times 10 to the second, we're going to say that it's either between 477, it could be about 478, it could be about 476. So what we're doing in general is we're widening our area of accuracy. So if we go back to the bullseye example from our other lab, think of that 10 was the center, but no, that 10 is going to be pretty big for us. So that is the reason for that is going to be the reason for why we use significant figures when we're estimating data. So, or when we're estimating calculations. So let's go to our uncertainty activity. And it tells us again what the lab is. And I was going to make a video of what is going to happen. This is just a little randomness. Don't worry. And so for this, I'm going to write it here. So the diameter of the Jolly Rancher was on average. If a video were to be shown, it'd show that Jolly Ranchers are not the most circular. So the average diameter was around 13 plus or minus 0.1 millimeters. And the height was around 29.2 plus or minus 0.1 millimeters. And then our mass, most people got around 6.0 plus or minus 0.1 grams. So if you are going, so the students who are not able to do this activity with us are going to use these measurements right there. And so I'm going to try not to keep this too long, but pretty much what you're going to be doing is taking all of this data, figure out first how many significant figures are are in each of them, because that'll help you. And then for my CP students, you're just going to do volume calculations with significant figures. Don't worry about plus or minus. On your paper, it might say plus or minus here, but that's we don't really do plus or minus too much. It's sort of implied when you're doing significant figures there. And then figuring out the density. So I gave you your equations right up here for volume and density. Volume of cylinder and density, and then once again for the CP students, use significant figures right there. So after that, you of course want to do an analysis. So what is the calculated density of a Jolly Rancher? How do these values compare to the expected value that I give you is 1.67 times 10 to the negative 6 grams per millimeter cubed? What are some ways that you could have improved your measurements? Another way of reducing uncertainty is to record and calculate these 4 more times. You're not required to do so, but why would that reduce uncertainty? And lastly is a learn on your own. So you're going to use the best estimate value as your experimental value and perform a percent error calculation with the number from number 2 as your theoretical or expected value. So that is a learn on your own. So use the internet, use whatever books you have at your disposal, try to try to figure out what I mean by percent error calculation, and then see what that nets you and how you can interpret that. So other than that, I appreciate your time, and I'll see you around.